Hi, and welcome back to part 2 of this is Freestyle 110, where we're talking about the design elements of SDN. Now, if you've watched the previous video, you'll have seen we did a fairly detailed recap, really, on what SDN is and how it's constructed and what the elements are. Shan't go into any of those, but you can see the elements in front of you here because we're going to cover these fairly quickly, hopefully, but the elements of underlay, of overlay, of control plane, and of automation that we need to make a successful SDN environment. So just bear with me a second while I bring my screen back up. So the first of the elements there from the list was the underlay, which is probably the most important part of the software-defined network, mainly because obviously it's the one that carries all the traffic. It's the thing that underpins everything. As much as we like to say that the network is the most important part of the IT stack because it underpins everything, well, the underlay, I guess, it is the same. It sits underneath absolutely everything, and if it doesn't work, then nothing works. Okay. So obviously, you know, the first things first, it's got to be fast. It's got to have the bandwidth in it and the entry points and exit points of the right size and scale to be able to really give people the performance they want to across that network. It needs to be reliable. And from reliable point of view, what we're talking about there is the obvious things about having no single points of failure, to be able to have the resilience in it to recover from a failure when there is one, and to recover quickly. Because if you think about what we've already said, the devices in the network have a requirement to be visible to a visibility engine, to an automation engine, to control plane, and so all the time there's traffic to and fro across that underlay, on which the network depends operationally to function. So the faster we can converge it if there's a failure, the faster, well, the less interruption we're likely to have to the service as a whole. Now, one of the other things we mentioned earlier also was that the state of the underlay will be pretty minimal. The idea is that each of the devices that sits around the edge of that underlay network need to be able to see each other, but really no more than that. Don't need to see any further out. And I'll just draw that just to explain what I'm saying there, I suppose. Let's say you've got a complex little network going on here. You can make this as difficult or as not as you like. You might cross-connect those guys and that guy. What we're not having to worry about here is where devices on the outside of that network, so PCs or servers or wireless APs or what have you, we don't care about those in the underlay. The underlay, get my drawing straight. The underlay is the green stuff here. The overlay is the orange stuff. The overlay is where we worry about where the users sit, where all that state sits. And the devices that sit at the edge of the network here only need to know about each other as far as the overlay is concerned. So as you rightly pointed out last time, Mel, we're worried about loopbacks across that underlay and the routing between those loopbacks, and no more than that. Mm-hmm. Okay. There are other elements to this. If you've got the internet and you're using the internet as a transport then you have to think about NAT and the effect that might have. For example, in an SD-WAN type scenario, you might have the internet as a centralized breakout of the internet from an MPLS network using user transport. Well, if you've got that as the case, and you've got all of your edge devices trying to hit a controller which might actually live in the internet, you could potentially have a problem there, because all of those devices will be going through the same internet breakout and thus have the same IP address. Those sorts of things are a consideration, and and there what it comes down to really is the fact that the underlay needs to be able to see both the set of services in order to function, right? So what do I mean by that? Well, if you think about it, if we've got the edge, all these devices that sit in this network, they need to be able to see things like the control plane, the automation engine. They need to perhaps see the internet, maybe. They might need DHCP or DNS services, all of those things. And so you have to then make sure that you're routing out of your underlay network into a point where they can get access to all those services. And it's quite a serious consideration, obviously, particularly if you've got wireless or whatever as well. You might have wireless LAN controller. You might have visibility server, all kinds of sort of central services that you might necessarily need to make it function correctly. Now, bearing in mind that orange overlay there is typically formed of a load of tunnels. What do we always have to worry about when we've got tunnels? MTU and MTU. I mean, it's really, really, really important, isn't it? I mean, we all have countless problems with IPsec tunnels or with OTV or all of these things where we're using a tunneled overlay. MTU is always a thing. You've always got to make sure you've got enough space in those frames to carry those extra layer of headers. So
yeah, I mean, and that's actually something that's it's easy for us. It's kind of easy when you know how. So if you've got a lot of experience in like tunnels and all that, but say you were a fairly new engineer to networking or a trainee engineer, you might not even be at the stage where you've learned about MTU, but you might be deploying an SD-WAN. So it's really easy to deploy the SD-WAN. The tunnels might come up, they might not be referred to as tunnels, or probably not. So it might not automatically click. So somebody might be actually studying like GRE tunnels or IPsec tunnels and understand the fact that MTU overhead is a case in play. But if they're actually, I've got a new job, I've been in it like 3 months, I'm getting this new project to deploy SD-WAN, and I'm halfway through it, and then it's like your cat shouting in the background.
It is the cat shouting in the background, yeah.
So I guess let's hypothetical scenario. Yeah, I'm pushing out my first sites. All looks good. Everything's talking to each other. I can ping and all that, and then the site goes live and all the traffic starts getting dropped. It might not be so easy just to automatically associate that with MTU.
No.
If you're a new age engineer in your exciting new role. Or it might just be like, it's not always obvious, I guess, to any engineer.
I think it's really, really important, isn't it? That I mean, from certainly from my generation, the first experience of an MTU would have been IPsec tunnels, right? Where you're connecting two sites over site-to-site VPN, and you have to monkey around with MSS. And various mechanisms to make sure that you're not pushing traffic over there that can't be fragmented or whatever. That was always the thing, right? And that probably my first experience with it. And of course, the more and more we've started using tunneling technologies, the more and more it becomes an issue.
Yeah. Yeah, I mean, like, for example, when I first started working with OTV, you know, it wasn't until you actually, you heard about it for months, and then you just seen, oh yeah, this is actually a better way how to control layer 2 broadcast, unicast, multicast forwarding between two sites. Oh, this sounds great. It's really easy to deploy, and then you actually get into like deploying it, and you're like, all right, hang on a second, it adds 50 bytes on or whatever it is.
Yeah, how am I going to deal with that?
You get the OTV tunnel up, and then you ping, and it's all fine, and then you start dropping traffic, as I say, like so. And it's not until you start doing pings with the EF bit set and the and you set the MTU, and then you start seeing packets getting dropped or whatever.
And it's always that awkward stuff. It's always the UDP or whatever that you can't do anything about it either. You can't even manipulate MSN.
Sorry, not to labour the point, but yeah, it's definitely my point is that's a very valid point, because it might not be obvious. None of the SDN solutions, until you actually get into the nuts and bolts of deploying it. It might be mentioned or thrown in here and there into a presentation, but it's not going to be a leading factor where it's like, if you buy a solution, you have to consider MTU and make sure your network and your switches and your router and your core all support MTU. So yeah, MTU of X. Because if you've got an old switch, I've even had like 6500s in the past that have had line cards in it that they max out at 1500 MTU. You know, so
there's not much you can do about
that. Rolls-Royce switch at the time, and it didn't support like jumbo frames, for example, for whatever purpose. But
if you without jumbo frames, obviously that's going to cause you the issues right there, isn't it? So no, absolutely. So I mean that leads us quite quickly onto the overlay side of things, I suppose. And like I say, typically that forms up as a mesh of tunnels. So obviously think about how that forms and what the scalability of that solution is going to look like, because if you're talking about tunnels and you're talking about particularly over the internet and what have you, you're talking about encryption. And if you're talking about encryption, you've then got to consider that your hardware platform that sits on the end of those tunnels is only going to be capable of a certain number, right? You're running software on these boxes. You only going to be able to build tunnels to a certain number of devices, and so you may have to think about changing the topology of the meshes of tunnels in order to minimize that impact. For example, I mean, I've got the our little orange network down here. It may be that, for example, we have a whole load more devices in another region potentially, or what have you, that all need to join this software-defined network. Now, obviously, I won't draw all the connections in because that would be silly. But if you now decided you wanted to build the overlay into there, what you might choose to do instead is create a separate overlay environment, so that you build your mesh of tunnels between these guys, and you're limiting the size of that mesh, because if you then had to build that out into the orange side of this network as well, obviously you're increasing the number of tunnels that has to be created. You start getting into sort of exponentially increasing those numbers. And that's problematic.
To put this into a real life scenario, then, Dan, would this be like the yellow would be like a WAN and the other color would be like a data center or a LAN, or are you talking about
potentially?
two LANs that might be plugged together, or what?
It may be two areas or two WANs. If you think about it, it may be, let's say you've got a large retail WAN, or a large retail site WAN of say, I don't know, 500 locations in the UK. Okay. What you may choose to do is say, well, actually, if I've got 500 locations, am I going to allow that to build out from every single one of those sites tunnels to all 500 of the other locations, or is that going to cause my hardware platform issues? What you might then look to do is regionalize it and say, well, actually, what we'll do is we'll have a north, we'll have a south, we'll have an east and a west, and then we've only got a link to 125 locations each, and then you have like regional hubs that are interconnected.
Yeah, by potentially an SDN core. So you might have an SDN core between
exactly
four regional data centers, and then off each regional data center, you've got the 500 sites in each region. So
exactly that. So you're basically creating a topology of tunnels because you're limited by the scale of the hardware platform. Yeah. But then you might want to be, because you might not want a whacking great router in every single little retail store. So this is where the balance comes into play. This is CCDE stuff, right? Isn't it? This is the compromise. This is where what you're doing is you're looking at the environment saying, right, the optimum would be to have this whacking great router because I need it to connect to all these places. But from a financial point of view, it doesn't make sense, and from so many other reasons about the management of them and so on. So you make a compromise, and the compromise becomes the regional topology. So that's important consideration. You've also got then to think about security of those that environment as well. Because again, some of those, if you're doing this across an MPLS network, you may have the option of not forming tunnels at all and just routing stuff natively, depending on what technologies you've got to play with. So, but if you are using a public network, you've got to look at what type of encryption you're using. You've got to look at how you deliver certificates to the devices and those sorts of issues. So all that's got to be considered. On top of the overlays, we've already talked about the virtual networks, and that bit becomes more fun, I suppose, to an extent, because what you're now doing is you're mapping services from a customer directly into these virtual networks and looking at how the segmentation works. And not just from a security point of view, but also from a policy perspective, from a customer's requirements, really. So this becomes something much more tangible that they can understand and appreciate. Nothing too much more to say on that one, really, other than consider what compliance requirements a customer might have. PCI, GDPR, blah, 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 those types of things. Consider where, from a straightforward security perspective, I suppose, from preventing denial of service, just that minimizing fault domain stuff again, looking at all of those sorts of options. That's how you break down those virtual networks.
So if you were to draw a parallel to the equivalents in the current or traditional networks, is the overlay like a VRF, and the virtual network is like, is the overlay like segmentation, and then virtual networks micro segmentation, or is it the virtual networks or the equivalent to a VRF, or does it vary?
It's an interesting question. I think it does vary. It varies on the platform, and it varies on the software versions, I think, as well. But I think in my head, I kind of look at it a little bit differently to the way some of the documentation and some of the platform sits. the virtual network is the equivalent of the VRF for me. So imagine in an MPLS network. Actually, an MPLS network is quite a good comparison, really, because obviously what you've got is to some extent you have an IP network that sits underneath everything. Then you have your MPLS tagged overlay, I guess, that sits on top of that, and then you have your VRFs on top of those, and that kind of, for me, that mapping works best, because so really, as far as the virtual networks are concerned, the overlay is actually its transport, and the overlay, as far as it's concerned, the underlay is its transport. If that makes sense. This is where I drew the layers in the last video.
Yeah.
How that comes together. So, but for me, virtual networks are very much to be consumed the same way you would consume a VRF from a customer perspective.
Okay.
And so that actually is a good point, because at some point those virtual networks need to break out to stuff. They need to be able to break out and consume some of the services we talked about in the underlay. So things like DHCP and DNS and those sorts of things. They might have to consume services that are in the data center, which might sit in an existing network. And so they're sort of connected back to the same places that the underlay is connected to. Now, so there's a security thing there of worrying about, right, well, do you bring those devices back and route them, allow routing between the underlay and the overlay, or do you have a firewall that sits between the two and prevents you getting from one to the other? I suspect that's probably the best approach myself, but obviously that ability to consume services regardless of where they are, and that service might include, as I've already said, things like DNS and DHCP, but it might also be a centralized internet breakout or cloud connectivity or something similar. There's lots of reasons why you might need to break out of that SDN environment, and so that needs to be considered, because at each virtual network you're going to have a border from that virtual network into the wider network, and each one is going to have to interact in a different way, and some may be isolated and never need to go elsewhere. We've talked about IoT potentially as an example of a virtual network. Well, what better security than actually don't connect it to anything other than within itself, and so you can't use it as a jump off point then to get to anything else. So yeah, those are important considerations, I think. Right, so moving on to the next element on my list is the control plane. And I've already talked at length about the fact that the control plane consists really of a centralized server, but also distributed state through the wider network. Now, what you have to consider is that those things collaborate, right? You've got the centralized server needs to see the switches and the routers and switches need to see the centralized server in order to maintain a workable state. So obviously that then becomes a requirement on the underlay, really, to make sure that the latency is kept to a minimum between the two, and B, that it's highly resilient is the connectivity there. So that's really, really key. You may have a number of collaborating elements within that control plane, right? It may not just be a server, a central control plane server. It might also be a security device like a Cisco ICE. It might be a wireless LAN controller providing part of that control plane state, and so on. So there's lots of potential links in the chain. In Cisco SD-WAN, you might have to consider, yes, there's the vSmart, which is the control plane. There's the vManage, which is the management plane, and the vBond, which is the orchestration plane. They all have to interact with each other, but also with devices across the underlay and the overlay. So it's all of those parts need to be considered, and they have very specific requirements in themselves. Again, we have the scalability question. Those control plane elements that make up the overall distributed control may have scaling requirements. They may only be able to handle a certain number of locations, for example, or they may only be able to handle a certain number of virtual networks, or a certain number of endpoints, or a certain number of network devices. Or again, there may be latency requirements there. It may be that you have to have a control plane element on every site. So these kinds of things are really, really key, and obviously are going to be dependent on the solution you're deploying. So there's a different requirement for each one. And then I guess the other part, the control plane, that becomes really critical is the policy definition. And this comes really with the virtual network stuff we talked about before. This is the bit where you go to the customer and you're talking to the customer about, right, actually, how do you want this to work at the virtual network layer? How do you want traffic to be routed? Would you prefer it over this type of link or that type of link? What are the latency requirements of these applications? What's the security requirements for these people to be able to talk to those applications, and so on and so forth. It's those things that you need to really fully appreciate and understand before you can implement the control plane accurately. There's always, as there is with any security type elements, there's always the option of deploy it with a wide open policy, and then come back to it later and start tightening the policy. That's it's like deploying a firewall within any rule, isn't it? It's like, yeah, do you do that? Some people do, right? But you've got consideration there and control that needs to be put in place. So cool. So the last real element to it is the automation, and we'll whiz through this. And really, as far as this is concerned, the whole point of this, any SDN really, is that the config is way too complex to try and manually maintain. So really, the goal of the automation layer, if you like, is to remove the opportunity for human error, really, as much as anything, by removing manual configuration. There are always going to be times where you do need to do some manual config. We talked already about how we interact with the existing network, how we do the migration activity. That stuff will need to be done manually. Can't avoid that. So that you need that capability to do some manual config, but as little as possible, obviously.
Makes sense.
And with that comes things like zero-touch provisioning, the templated configuration that you can just connect something to the underlay and up it comes and just joins the network. That's really a really useful part of this. But typically the automation controller or the automation server, whatever it is, doesn't have the same requirement for connectivity that perhaps the control plane does, because obviously it's only important at a time when you're provisioning the network or provisioning changes. Typically, if you lose sight of the automation engine, you won't be able to make changes on the network, but the network will continue to function. So from that point of view, it's less critical operationally.
So that's similar to like if you just and most people watching this will be familiar with Meraki, which is one of the first SDN type solutions, policy based solutions, I guess, that I probably dealt with. I think earlier on I mentioned in the first video I mentioned like SD-WAN and I-WAN and ACI. But actually, Meraki was way before that, and that was probably the first software-defined network that I worked on, way back in probably 2012, 2013, before they were acquired by Cisco. And I guess where I was going with that was that if the Meraki cloud is inaccessible, your network still operates, but you have no in that case, no visibility into it, and no ability to push changes out. But yeah, so that's where you start looking at things like, I guess it's evolved now to Meraki just being a cloud-based SDN controller. Like other solutions are now catching up. So I think you've got Viptela cloud-based controllers and other. I keep calling it Viptela like 2 years after they've been acquired, but
it's
what I mean. Like
it's easier than calling it Cisco SD-WAN, because it's the term SD-WAN can mean so many different things, can't it? So I think
cloud-based. I guess what I was saying was like the just to touch on the point of less critical operationally. So it's less critical operationally from the perspective that if it is inaccessible or not online all of the time, where that's obviously preferred. But if it's not, your network's not going to die, but you're not going to be able to probably monitor it, push changes out and things like that.
Exactly that. So and that's a really good example of it. I mean, in most instances, that automation element and the visibility element can drop off the network, and potentially the network will be not impacted, will continue to do exactly as it did before, and then hopefully when it comes back onto the network, it can just pick up where it left off. I've seen, as an example, DNA Center for software-defined access. Very, very similar. If it disappears off the network, it's a bummer because you can't see what's going on in your network anymore, but it continues to function. So, I mean, that's a part of that distributed state from the control plane point of view, I suppose, covers that as well. But purely, when you're talking about purely an automation engine, it's there for provisioning. If you're not provisioning anything, you don't have to have it right at that moment. So you've got more flexibility with its connectivity. And I mean, the one last thing that I wanted to just mention on the automation side of things really is, and that's get rid of that, is that you can use it for orchestration of workflows. So if you think about building elements of the network to support an application delivery or whatever, that then needs to be incorporated into a wider workflow. So, for example, you've got a new application being delivered that has some firewall rules updated. It'll have some load balancer rules updated. It will spin up some workloads in the data center, whether that's in the cloud or wherever. But it also needs some policy changing in your SDN environment. Typically, that would be done through your automation engine using that orchestration capability, maybe API calls and that sort of thing. So really, then it's a case of considering, right, okay, how does the customer deliver their orchestration? How would they consume that API, and how would that work for them? It's a consideration that needs to be borne in mind for sure. So I think that covers it as far as I'm concerned. I think we've gone through a hell of a load of different considerations and options and what have you there. Was there anything more you wanted to cover, or do you think we?
No, that was really good. It was really good just to, I know we mentioned a couple of products and things like that throughout, but it was really good to just talk through SDN as a thing and not focus too much on, you know, the bells and whistles, what this does and which protocol that uses and all that kind of thing. So yeah, I definitely learned some stuff from that. So thanks for walking us through it.
It's a pleasure. Thanks for everybody watching. If you've got any comments or questions or queries, you know how to contact us. We've got networkfreestylers@gmail.com. You can get us on Twitter at netfreestyle, or obviously through the comments in the YouTube channel. Thanks very much.
All right. Thanks, everyone. Thanks, Daren.
Cheers.